Now let's start chi-square with a test for goodness of fit. Now the chi-square test for goodness of fit tests claims about population proportions. It is a non-parametric test that is performed on categorical data, that is data that is on the nominal or ordinal scale. So let's work with an example. In the 2000 US Census, the ages of individuals in a small town were found to be the following. We found out that 20% of the people were less than 18 years old, 30% were between 18 and 35, and 50% were greater than 35. So those are our population proportions. That's the distribution of ages we would expect to find in any given sample. Now, in 2010, the ages of 500 individuals were sampled, and below are the results. We have 121 people who are less than 18, 288 that are between 18 and 35, and 91 that are greater than 35. Using alpha 0.05, would you conclude that the population distribution of ages has changed in the last 10 years? So, we have our expected probabilities, and we have our actual observed values here. So based on these expected values, if we took a sample of 500, what would you expect the observed values to be? Well, if you expected 20% of those 500 people to be less than 18, you'd expect 100 to be less than 18. You'd expect 150 to be between 18 and 35, and you'd expect 250 to be greater than 35. So now we have what actually occurred in our sample of 500 and what we would have expected to have occurred in our sample of 500. And now we can do our hypothesis tests for a chi-square test for goodness of fit, starting with defining the null and alternative hypotheses. Our null is that our data meet the expected distribution, and the alternative is that the data do not meet the expected distribution. Alpha is going to be 0.05, just like always. Calculating degrees of freedom is done like this. We just take the number of groups we have and subtract 1. Here we have 3 groups, 18, 18 to 35, and 35. So we just take 3 minus 1 and get 2 degrees of freedom. We then use that to find our decision rule. We have this chi-square table where we look up alpha 0.05 with 2 degrees of freedom, and we find 5.99147. So we say, if the chi-square we calculate is greater than 5.99, we're going to reject the null hypothesis. Calculating the test statistic for a chi-squared is actually not that bad. It follows this equation right here, where we take every observed minus expected, square it, divide by expected, and then add everything together. So it looks something like this. For less than 18, we observed 121 and we expected 100. So it's 121 minus 100 squared divided by 100. And then we add the other two observed minus expected fractions to get our total chi-squared, which in this case is 232.494. Which brings us to the result. Remember, we're going to reject the null if it was greater than 5.99, and it definitely was, 232. So we will reject the null hypothesis and say that the ages of the 2010 population are different than those expected based on the 2000 population. The sample that we observed was different than the sample we expected to find using a chi-square test for goodness of fit.